but nevertheless. Now we will get into something very interesting. So now that a body, a rigid body is rotating, right? So, and for rotation, we have to identify the axis of rotation.
Yes, sir.
That is important. Okay. Now, under different circumstances, how we are going to identify many of the aspects involved as far as the rotation or motion of the rigid body is concerned. So now the question is how to locate the axis of rotation. How to locate means, now say this is a cross section, this is the cross section of a rigid body, and I suppose all of you know what is the cross section. So at point D, you know what is the velocity. Supposing that is the particle D, what is the velocity, you know. Or yes, particle A, you know what is the velocity. Particle B, you know. Particle C. Supposing all these points, you know the velocities. Okay. So if you know the velocity of D, so you are representing that velocity by this vector. What is this? This vector is VD bar.
Yes, sir. Yes, sir.
Yes. And you see VD bar. So we don't know whether the center is here. Okay. And supposing the A vector is given, VA bar is given. VA bar is given, VD bar is given. And supposing it is said that both of them are along the same radius. I mean along the same radial path. Okay.
Yes.
Then you see the tip of this vector, if you draw a straight line, that straight line should pass through the axis of rotation or the center of the circular path. Okay, and similarly, if you know this C, it is passing through this. Okay, see, because what is the condition? Supposing this is the center of all these circles. You can see here 1, 2 circles are the center of both the circles, and the what is that common here? You see, for all these particles which are rotating, you please appreciate and understand. One thing is common. What is common? Omega is common.
Yes, yes.
Okay. Yes, now please appreciate. Omega is common. That is, the D rotates with omega with respect to A.
Yes.
D rotates with omega with respect to C. Hello, and
sir,
D
omega with respect to
omega with respect to listen. That's what I'm telling. See, now this line itself, COAD, this line itself is rotating with omega.
Yes, sir. Yes, sir.
You understand? This line itself is rotating with omega. So any point on this line is rotating with omega understood? Is also rotating with omega. That is, you see this line. This whole line is rotating with omega. Now with respect to what? You draw one reference, and what is omega? D theta by dt.
Yes.
Okay, so let me put it. Okay, so let me. Okay, see here. See, for us, you take any body, you have drawn any line, any arbitrary line. I drawn an arbitrary line, okay, and I drawn an arbitrary line, and I have drawn a reference line. I can draw any reference line. This is a reference line. Now, this line itself will move through an angle d theta. Okay, in time dt. So therefore, this will be d theta by dt will be omega. See, this whole line itself will rotate by omega. Any line, you can take this line will rotate like this, or if you say I have taken this reference line AB, this, and at the same time I will take another line here, say CD. So if this line rotates by d theta, this line will also rotate by d theta.
Okay. So the line you have considered, sir. COAD and the points.
No, wait. Let's come to that point. Let's come to this point. See here, this line COA, itself. Okay. So this line COA itself, you see, if you take that as a line, that line itself is rotating omega.
Yes. Okay.
Understood? Now the question that you are going to ask is, you are asking is, say now I have drawn one line here. Say this is C O A D. C O A D. Now this line itself is rotating. Say at some point of time, this line itself will become like this. So this angle is d theta. This angle is also d. Correct?
Yes.
Hello.
Yes. Yes.
Now you see, through supposing you have taken here with respect. See now here the center of the circle. Sorry, I have drawn it wrongly here. So I draw the right line. Okay. So with respect to center, whether this point, so we take the COAD. Okay. With respect to this O, this has also gone by theta, this has also gone by theta, this has also gone by theta.
Yes, sir.
Correct? All these three are thetas.
Yes, sir.
Hello?
Yes, sir.
Yes, sir.
So therefore you see the angular velocity of every point on this line is the same.
Yes, sir.
Hello, are you with me?
We are with you.
Yes, sir. Yes.
Yes, sir.
Okay. So if you take this radius here, then the omega for all is same. So the velocity of this point will be omega into OA. Okay, and the velocity at this point will be omega into OD. And the velocity at this point will be omega into
OC.
But of course, this OC vector, if you take the vector, this velocity vector will be down, this velocity will be up, this velocity will be up. You can see here, OD is larger than OA, therefore this velocity vector I am showing it by larger.
Yes. Yes.
Yes, sir. Yes.
Okay, and many things like this. Many things like this. Okay, so you can see that the from the velocity vector. Say now in general, if I give you some particle, say if I take here, say if I give you some particle, and if I say this velocity vector is this, okay, then where is the center of rotation? If I ask you, so one thing is sure. What is sure? That you draw one line like this. See, this line is perpendicular.
Yes, sir.
So the center is somewhere here.
On that one.
You can appreciate it.
Yes.
The center is somewhere here. You don't know where it is. Okay.
Yes.
Now supposing I give you one more particle. So this is having some velocity. This is having another velocity. Say this is v1 bar. This is v2 bar. So you know for sure that you will just drop a line perpendicular.
Yes.
So where those will intersect, that becomes the center of rotation.
Okay.
And then if this is a body, and this is a cross section of a body, so the axis is passing through this center of the circle. Because I hope you got it.
Yes, sir.
That's simple. That's simple. So therefore, but you see, you take any particle here, all these particles will have same angular velocity or angular acceleration.
Yes, sir.
Yes, sir.
Okay, I suppose this is quite simple to comprehend. So based on that analogy, you can now see here that VA is equal to omega into OA and VD is equal to omega into OD, cross product. Okay, so it should be omega. See, VA is equal to what? Either into cross product or is it simply a multiplication? Simply multiplication because both sides are scalar.
Yes, sir.
Okay, easy to comprehend. And there is another way to identify it. That is the tip of these vectors. That is the tip of vector VA bar and VD bar and the tip of vector VC bar. If you see there, all those tips are also passing through the center of the circles, or it is passing through the axis.
Sir, cross product only, no, sir? By simple multiplication. We define V bar like that.
Correct, but here I didn't write here VA bar, man. If I had written VA bar, then and it should written omega bar, then OA bar.
Sir, however, if you write even bar also to be scalar product of this.
Anything?
Even if you write their bar also, sir, then also it will be scalar product of this.
Hang ಮಾಡ್ಬಾರ್ದು. See, okay, sin theta is 90 there, fine. It is 1 and all fine. But speaking in those terms, because bars are not written, I am treating it as a scalar. That's it. Scalar, see this, this symbol in this case, what is it denoting? Is it cross or simply multiplication, I asked. So since all the quantities around the cross are scalar quantities, it's a scalar. That's it. Okay, done. Okay.
You told that in that line COE said the points with respect to other points also having same angular velocity.
No, I'll come to that one. I'll use a different figure and explain it. I'll use a different figure and explain that. Okay? Okay, fine. I suppose you understood this.
Yes.
Right. Okay.
Yes, sir.
So in this circumstance, now let's come to another diagram here. So in this diagram that you see here, you can see particle 1, 2, 3, 4, 5, 6. You can see all these particles.
Yes.
1, 2, 3, 4, 5, 6.
Yes.
So one at the point 1, you can see that there is a velocity vector, velocity vector, velocity vector, velocity vector, and these dotted lines that you see here, okay, they are the lines that are drawn perpendicular to these velocity vectors.
Yes, yes,
Okay, and you can see those lines are all intersecting at this point. Okay. Now the question here is, as you can see, this body as you see is in motion. Hello.
Yes, sir.
Yes.
Now I didn't say it is rotatory motion or translatory motion. It is having both the type of motions. Okay. See, this body is moving like this. Assume. Okay. So it is moving, man. See, this phone is moving. Right. So what type of motion is that?
Translation and rotation.
Combination of rotation and translation.
Yes.
So now at a given instant of time, if you freeze the time, okay, if you freeze the time, that is you are taking a snapshot at a particular instant of time, then at that instant, if you are taking a snapshot at that instant, okay, we will create a concept called instantaneous axis of rotation. Instantaneous means for that moment only, assume that this point is at rest. For that moment only.
Yes.
That moment only, you assume that point is at rest. Okay.
Which point?
This point.
No, I mean that point is.
No. See, okay. Now at a particular instant of time, you have just taken a snapshot. When you take a snapshot, what are you going to capture? You are going to capture the velocity vectors of each of them.
Yes.
That is intuitively.
Yes.
Okay.
Intuitively, you are capturing all of them. So that means now, when at that instant, all these points are at rest. Assume at that instant, all these points are momentarily at rest. But we can't say all of them are rest, and I can't write these velocity vectors.
Yes.
If I write these velocity vectors, okay, then I can't say the body is at rest.
Okay.
So, however, I create a concept here that at that instant, this point is at rest. Okay. Now,
So that you are telling or
I'll tell you very clearly what I mean. This is a concept that is created here. This is a concept that is created here. Okay. Now, please read this. In a pivoted rigid bodies like rotating fans, doors, etc., the bodies have permanent axis of rotation. In combined motion, we cannot have fixed axis of rotation. However, there may be a point inside the given body or extended body which is at rest momentarily. See, this is a concept. This is a concept created because we want to separate the combined motion into two motions: translatory and rotatory. We want to momentarily split them into two. So we create this concept called a point which is this instantaneous there. This point is called instantaneous center IC. The axis through this point is perpendicular to the plane of rotation. which we call it as instantaneous axis of rotation, IAR.
So when I take snapshot, how will I identify?
Okay, forget snapshot. See, if what I was trying to say here is, at an instant of time, if you are able to locate these velocity vectors, okay, and you have if these velocity vectors at that instant of time, and if you drop perpendiculars from these vectors, then it will pass through a point which you can consider at the, which is definitely the point. It is a point where all the particles are rotating about that point.
Yes.
Okay, so for all practical purpose, this becomes the center of the circles or the axis passing through it. But since the axis is actually also traveling, it is also moving. Okay. So therefore, it is also traveling. So therefore, we say, okay, Baba, for a moment you say it is at rest, and let's understand the rotation about that point, and then we will also give the translatory motion to that.
Okay.
That's the whole idea.
Yes.
That's the whole idea. Okay. So we create the concept called instantaneous axis of rotation. Okay, friends.
Yes, sir.
Now this you can find it in many situations. Now you can see that there is a rod that is kept on the wall, and assume that this is frictionless wall. There is no friction between the two. So if you keep a rod like this, as you know, this rod starts slipping. That is, this end of the rod will start moving along this ground, and this will start sliding along this wall. So the velocity at this point will be VB bar. The velocity at this point will be VA bar.
Yes.
Now what you see here is that this rod, as it is sliding, you can see, if you take this as a line, this rod that is sliding, it is changing its orientation.
Yes.
Yes.
So it gives us the concept of rotation.
Yes, sir.
It gives us the concept of rotation.
Yes.
Now what you will see here is that this is the velocity vector at this point, and this becomes the velocity vector at this point. So these velocities, and if this body is rotating at a particular instant of time, these velocity vectors are not constants. VA bar and VB bar are not constants. They will change because the gravity is acting, force is acting on this body. So when force is acting on this, because of that force only it is sliding.
Yes.
So therefore there is acceleration. So VA, VB are not constant, but at a particular instant of time, you say this is VB bar and this is VA bar. And since you also see that the orientation is changing, then the concept of rotation has to come into picture. And if you bring the concept of rotation there, then you have to bring the concept of the axis of rotation. In or the center center or which the two ends are rotating. You have to bring this. Now the question is, where is the center of rotation? Or in this case, at a particular instant, where is the center of rotation at the particular, or where is the instantaneous axis of rotation passing through? So going by whatever we have understood, just draw a perpendicular here and just draw a perpendicular to this vector. They both meet at this point. So this becomes what? The instantaneous center of rotation at that instant. Okay. Now you can very well see why I am calling it as the instantaneous. Why I am calling it as the instantaneous rotation.
Yes.
You can very well see. Okay, so why in the world we should call it instantaneous? Because you can see that at one instant the rod is like this. So this velocity vector is down, this velocity vector is here. So the instantaneous center is this. So this becomes IC1. Okay. At the next at some other instant of time, the ladder is like this. So this is the velocity. Correct? Hello?
Yes, sir.
Now again you drop the perpendiculars. So now this becomes the instantaneous IC2.
Yes.
So you can see that the IC is changing.
Yes, sir.
IC
Yes,
is changing. Okay, the instantaneous axis of rotation is changing. That is why it is at that instant it is here. At some other instant it is somewhere else. And this is how you are going to locate. Okay.
Yes.
And yes, now you see this entire rod. This entire rod is undergoing angular motion.
Yes.
This entire rod is undergoing angular motion. That is, if you say this is theta, okay, and as it is proceeding here, say this is theta 1, this is theta 2. And therefore, this rod itself is undergoing angular acceleration. That is, d theta by dt is continuously happening till it comes flat.
Yes.
Fine? So this is got omega, and omega is same. You see here. Now what you have to see here is the omega of at this point with respect to this point. So now see with respect to this point. Say this point is A, this point is B. The omega at A with respect to B. Okay, anyway, I'll show another diagram. I hope you understood instantaneous axis of rotation.
Yes.
Okay.
Yes.
I'll go for another diagram that will be clear. Okay, fine. Okay, I'll just give you a minute. You can just go through and satisfy yourself because I'm going to use this diagram again and again.
Excuse me, sir. Sir, this axis of rotation, should it be always parallel to the planes, like always, perpendicular to the planes?
Yeah, see, if the two velocity vectors are in this plane, no?
It is in cross section. So
No, it is the cross section. See, these two velocity vectors are in the same plane. Hello?
Sir, but if you take like...
See, listen, these two velocity vectors are in a plane.
Yes, sir, yes, sir.
If these two velocity vectors are in a plane, okay, then the axis of rotation must be perpendicular to this plane.
To the plane, sir.
To the plane. To the plane containing the two velocity vectors.
sir, always cross section.
What cross section?
The plane should be always cross section. Or else if we cut it like this, then
Listen here, listen. Now, don't make it very unnecessarily complicated.
okay.
So, there is a plane which is containing both the velocity vectors. Okay, the axis must be perpendicular to this plane.
Yes.
Over. Don't unnecessarily bring a cross section into all here. Not necessary, not necessary. See, if it is necessary only, you should bring it. Okay, Dimant. Hello.
Sir, yes, sir.
See, when you ask a question, if you are satisfied, you should say yes. Okay, otherwise I'll keep wondering what is going on. Now, let's take another condition. Okay. Now here you see finding instantaneous axis of rotation when V and omega are given. Say this is a body. Okay, at a particular instant, the angular velocity is given, and there is a point here. Okay, what is this point? A is a point where the velocity Vc happens to be what? The center of mass.
Yes, sir.
Or com or center of mass. Sometimes it is written as CM. So if I give you the velocity of the center of mass, so velocity of the center of mass means you will place the velocity vector at this point. And this whole body is rotating, omega. Hello?
Yes, sir.
Yes, sir.
Okay, Then again you see, where is the center of rotation? The center of, see, I hope you understood, this body, the center of mass of this body is at A.
Yes.
Okay, right? And this body is translating, I mean, at a particular instant of time, the velocity vector associated with the center of mass is V bar. Okay, and this whole body itself is having a rotation omega. Hello?
Yes, sir.
Yes, sir.
That is again this. Okay. Now, at a particular instant of time, where is the instantaneous axis of rotation there, or where is the instantaneous center? IC, or if you determine IC, then IAR will be perpendicular to that. That's the question. Very simple, very simple. Again, from V bar, you drop a perpendicular. Okay, so you are dropping a perpendicular from V bar. Suddenly, all of you are moving on.
Yeah. Yes, sir.
So this was the body given. So this is the center of mass. So this velocity vector is given, and omega bar is given. Omega bar is given. So we have to locate the center of rotation, or instantaneous center we should find, and thereby we have to determine IAR, instantaneous axis of rotation. So one thing is for sure. So if you drop a line, okay, what is this? This is a line I have drawn perpendicular to V bar. So the IC is somewhere located on this line. Hello.
Yes, sir. Yes.
So I will arbitrarily choose this point. I will arbitrarily choose this point. Okay, this point O. Now, and I will say this distance is R. This distance is R. And now we know V is equal to omega R. Correct? Hello. And now we want R. So R will be equal to V by omega. Both these quantities are given. So from this point, which is the center of mass, I can locate this point, which is the axis of rotation. So this becomes the instantaneous center of rotation, and this is the center of mass. Okay, and this is V1. So this is how you can locate it.
Yes, sir. Yes.
Got it?
Yes.
That will be instantaneous.
Yes.
You know?
That will be instantaneous center.
But instantaneous center of rotation.
Oh, okay.
That is center of rotation. So now you see, center of mass is separate, geometric center may be different, center of gravity may be different, right? And you have got now another thing, instantaneous center. And an axis passing through it becomes instantaneous axis of rotation.
Yes.
Yes, sir. Right? Okay, fine. Right. So we will go in steps and understand a very complicated motion. Okay, in stages.
So why can't it be above the center of mass?
Yeah, it can be above also. You are right. You are right. It can be above also. Nice question. Okay. Now somebody would like to comment on her. Comment about what she has told here now. Why it can't be up?
Sir, omega dash. Yes, sir. Sense of rotation will be opposite, sir, if we take above the center of mass.
Got it? Got
Yes,
it? Huh? So if omega was in the opposite direction, as it is shown. Hello, if omega was in the opposite direction as it is shown, it would have been in the upper direction.
Above, yes, sir.
Yes, sir.
So therefore here you see, the difficulty in mechanics, see now in other subjects relatively, mechanics, how, see, like for example, you had a doubt here. So you should understand the mechanism of rotation, mechanism of interlink, there are some things like that. So you should get a feel of those things. Okay, right. You will get it gradually, as we proceed, you will get it. But that's a nice question to ask. I appreciate it. Okay. So now one more aspect is, the velocity at P. See in this case, the velocity at P in this case. Okay. The velocity at P. What will be the velocity at P?
0.
0.
Yes, sir.
Yes, sir.
Instantaneous.
Yes.
Okay, because you have said it is momentarily at rest.
Yes, sir.
Yes.
Now here is another typical case when velocities of any 2 points are given. So here A is given, B is given. So what you will do, to this velocity vector you will drop a line perpendicular. To this point you will drop a vector, and both of them are meeting here. So this becomes what? The instantaneous center of rotation.
Yes, sir. Rotation.
Got it?
Yes, sir. Yes, sir.
Yes, sir.
Anyway, I'll just pause for a minute to just run through. Okay, so what is omega here in this case?
So,
Where, sir?
In this case, what is omega? In this case, what is omega of this? I give you to VA. What is omega? Omega is equal to what?
VB into PB is equal so VB by PB is equal to VA by
So VA by AP is equal to VB by VP.
Yes,
Omega is equal to VA by AP is equal to VB by VP. All these relations you remember, they will all be handy because these are all part of some bigger problems, bigger numericals, bigger things that we are going to learn. Now typical case. See, when two given points move with parallel velocities. Again, you see, this is a bigger body. I have identified 2 points here, A and B. A has got velocity VA, B has got velocity VB. Okay?
Yes, sir.
Now again, these two are points in some rigid body in motion. Okay,
Yes.
so
Yeah.
so now here again you see you drop a perpendicular from here, you drop a perpendicular from here, but then you will not get the intersection point. Hello.
Yes,
So
Yes,
then
sir.
then there is one more technique that you'll use. So this VA bar vector you will draw VB bar vector because I have given you the velocities at these 2 points. So then when you join tip to tip and also this particular perpendicular line, they will all have meeting point here and this becomes the instantaneous rate.
Yes, sir.
And now supposing VA bar is given here and VB bar is ulta like this. Okay. Now also you will say the tip to tip and again perpendicular, they will meet at this point. Obvious.
Yes.
Okay, with a bit of common sense, you will feel that yes, this is how it should look like.
yes.
Quite interesting. Here, again, if you want to make some calculation here, okay, let me give you some thought process here. Okay. So, if I give you the two vectors A and B, and the distance between them as D, can you find out X in the first case and X in the second case? For X in the first case and X in the first case and second case.
Yes, sir.
Yes, sir. Yes, sir. It's a similar triangle setting.
Here are used.
Can you repeat the questions?
Can you get X man value of X? I given you VA bar, I given you VB bar, and I given you this distance D.
Okay, yes, sir.
Sure.
Okay, difficult. So we know again here what is common, omega. So VA upon D plus X is equal to VB upon X.
Yes, sir.
So you
Yes,
have to
sir.
do it for X.
D by D minus D.
You have to do it for X.
EBD by D. EBD by D minus DB. Yes, sir.
X is equal to
VBD by D minus D.
VBD divided by
VP minus D.
Yes, that's it. Okay, fine.
Yes.
Yes, yes, sir.
Sir, just excuse me, sir. Sir, like Sudheer was saying about similar triangles here. Like, how can we solve it using similar triangles?
You ask him man.
That's
Sir,
Yeah,
externally similar triangles.
See,
Ratio of
he will
sides.
take this one similar triangle and he will take this another similar triangle. Okay,
Yes,
and he
yes,
will
sir.
get the ratios there. That's all, ratio of the sides.
What I written is only
What I
this
have written there is only similar triangle only. You identify two things and do it.
after
Yes, sir.
Okay, fine. And for the other diagram, where this is given, this one. So again, this distance is given, B, VA and VB. Okay, so this is VA and this is VB, and this distance between them is D. Okay, so then you have to identify this X, or we took it this one, no? This X. This X. I think you can do it again. Again, you can use similar
Yes,
triangles.
BLD by BB plus BL.
Okay, done. Fine. Just that, a thought process. Okay. So I'll be taking you to the next way. So you slowly get used to this because we are going to now enjoy this, because now we are coming to the reality, because so far, everything was idealized. Particle is moving, a body is moving in a straight line, a body is moving in a circular path. Now, there is no stop. The body can move anyway, anyhow, and we are going to say, yes, this is it, this is it. So here you see, can the 2 points whose velocities are parallel be as follows? Okay, sorry, it should be VA. A should be suffix here.
It's okay.
So here. Okay, so can the 2 points whose velocities are VA bar, VB bar? So here, VA cos theta is equal to VB cos theta for rigid bodies. Is it correct?
No, sir.
No. Why?
Sir, if we draw a line perpendicular to V and VB, sir, they'll be parallel and they'll never intersect, so we'll never get shit in the center.
What is that I asked? See, in a rigid body motion, in a rigid body, can this be a possibility? VA cos theta. I didn't say anything, only I said rigid body. I didn't say motion and all. And VA bar VB bar is means it is motion. But can this condition be there? VA cos theta is equal to VB cos theta.
Yes.
Why?
Yes.
Why?
Because VA will be omega R, sir. VB will be omega RT.
See, no. See, the very basic concept of rigid body.
Sir, the distance between 2 points.
Yes, the distance between them will not change. That is, see, what is VA cos theta? Okay, it is a component of velocity along that line joining along the line AB, correct? And what is VB cos theta? The component of B along the line, correct?
Yes. Yes.
Now, VA cos theta minus VB cos theta. VA cos theta minus VB cos theta is equal to 0 according to this equation.
Yes,
Huh.
sir.
So what does it mean? The velocity of A, okay, with respect to velocity of B.
Yes,
That is
sir.
the component of the velocity of A along this line with respect to B. Okay, it cannot change. It cannot have a relative velocity because
Yes, sir.
VA and VB cannot have two different velocities along the line joining the two.
Yes.
Yes, sir. Yes.
See, such a beautiful thing, huh?
Yes.
Along the line joining the 2 points A and B, along the line joining the 2 points A and B, there cannot be relative velocity between the two velocities along the line joining A and B,
Yes.
because it is rigid body.
Yes.
I suppose all of you captured it.
Yes.
Yes.
But the velocity of point A can be different from velocity of point B. Yes. Isn't it? See, this particle can have different velocity, this particle can have different velocity. But along the line joining, okay, they cannot have their components of velocity along the line joining the two cannot be different. They have to be same. Okay, you want me to explain it, right? Fine, sure. See, now this is a rigid body. I'm just taking 2 points, A and B. So this distance between them is fixed. This distance between them is fixed. Okay. Now I am going to explain this concept like this. I am drawing a line here. Okay. I am drawing a line here. Okay. Now, if D is always constant, D is always that. What is D? The distance between these 2 points. Now, supposing this component of the velocity I will take it. So I will say that this is moving with V1 bar and this is moving with V2 bar. This is moving with V1 bar and this is moving with V2 bar. Is it possible? See, if V2 is greater than V1, then this will move closer to this.
Yes, sir.
If V1 is greater than or equal, then it will move closer to this, but it cannot.
Okay.
So this condition is, so here in a rigid body, V1 bar has to be equal to V2 bar. It cannot be anything other than that.
So, what is this V1 and V2, sir? They are the velocity of the...
Where are you? When I said that this is a rigid body,
Okay.
did you hear me?
Yes, sir.
And these are 2 particles in a rigid body. Did you hear me?
Yes, yes.
Then I have drawn a line joining the 2. Did you hear me? Then I have drawn 2 vectors, velocity vectors on the line.
Velocity vectors along the line.
Along the line, I am not seeing it.
But they are not the actual velocities of the...
Assuming. See, here I am telling now, I am giving a condition. I am giving a condition. The velocity at this point is V1 bar, the velocity at this point is V2 bar.
Okay.
Okay, now what can be the relation between V1 bar and V2 bar? They have to be equal.
Yes.
There cannot be any other relation.
Yes.
Okay.
Same rigid bodies.
Got it now? Hi.
Yes, sir. Yes.
No, okay. Just deeply thinking. See, but this can have some other, see, this can have velocity in this direction, this can have some velocity in this direction. That is possible.
Yes.
Okay. So what you see in this diagram is that the 2 points A and B have 2 velocity vectors. The 2 velocity vectors are there, VA bar, VB bar. But the component of this and component of this, they will always be equal. Okay. But that component will be equal. And therefore now if you take the components of this along this, then another component will be perpendicular to this.
Yes, sir.
VA sin theta, VB sin theta. They can be different.
So you told this for any type of motion of the rigid body.
See, what did I say? Any type of motion and all? Did I say anything like that? Did I say anything like that?
It can be for any motion of the rigid body. You told us.
What I said, I am only telling you that this is a rigid body, right? There are 2 particles. I am considering 2 particles of a rigid body. The velocity, I am drawing a line AB. Okay, and if I say this the velocity along this is V1 bar and the velocity along this is V2 bar, what is the relation between V1 bar and V2 bar? V1 bar must be equal to V2 bar. You understood that point? That's all. What is your confusion?
Say reason. Okay.
What is your confusion, you tell me?
Say no, sir.
I say, nothing. No, I didn't say anything more than that.
Okay.
Okay. Now, see, now the condition is if VA bar is equal to VB bar in this diagram. In this diagram, if VA bar is equal to VB bar in this diagram, then what have you got to say? See, this body is there. This point is having VA bar and this point is having VB bar and both are equal. Then what will happen to this
The
body?
body is
Translating.
It only have pure translation.
Then
Pure translation.
starts. Yes.
It will have pure translation.
Yes.
See, you have to start abstracting like that. So it will have pure translation and theta is equal to 90. Then VA bar. So okay, next condition is, see, VA bar is equal to VB bar, then it is pure translation. Next condition is if the angle is 90 degrees. So here you see here the next condition I have given is VA bar, okay, and VB bar. Okay, if both of them are equal, then this will only translate.
Yes.
Okay. Now the thing is, supposing now I have a condition where this is BA bar and this is BB bar. This is BA bar and this is BB bar. Both are perpendicular to this line, joining the two.
Yes.
So this is A point and this is B. Okay. Now what happens to this rod? What supposing what happens to this? What happens to this body? See, I am showing the velocity vectors at two particles. This particle and this particle. Or you take only one rod. Okay, you take this rod. To this rod, if this is BB bar and this is BA bar, what happens to this rod?
It is not against.
See, you see, no, I have written BA bar more, BB bar less.
It will rotate to clockwise.
It will rotate.
It will only rotate. It will not translate. Yes or no?
Yes.
Yes, sir.
Come on, yaar. It will have both. It will have both. It will have both. Understand? It will have both. Okay, it will have both the type of motion. It will also translate and it will also rotate.
It can have both or only rotate also.
This is a rod. So
This is the rod, I said. This is the rod. Wait, what is your question? What is your question?
Okay, that is a rod, sir. Okay, sir.
This is a rod, then it will translate also and it will rotate also. Isn't it now? See here. I pull this. So it will, because of this pull, this will move like this. But then this will also rotate like this. We'll take a numerical and understand this better.
Sir, one also. Sir, only at this instant, the velocity of A and B are like this, sir.
See, whenever I write VA, VB, it is at instant only. Unless I said it is uniform velocity.
Yes, sir.
Unless I specified. Understand?
Yes,
Unless specifically. Say expressly specified, it is this. Okay, fine? Hello?
Yes, sir.
Yes, sir.
Now, some difficult situation. Since the instantaneous axis of rotation is at rest with respect to ground, okay, you can imagine that a body is moving, the instantaneous axis of rotation is at rest with respect to ground. That is how we have analyzed.
Yes, sir.
Are the frames attached to IAR and ground equivalent? Frame of reference. So what I mean here is, so if you take a body in motion, so you have found out that this is IAR, this is IAR, okay, and of course there is ground, right? So the ground reference. So this is the reference of the ground, and I will consider another reference point here. To this point here. Okay. So what we have now said is that this IAR is at rest with respect to ground.
yes.
IAR is at rest with respect to ground. Okay. And I am drawing two frames of reference. One with respect to this, one with respect to this. Okay. Now read the question. Are the frames attached to IAR and ground equivalent? That means,
Yes.
wait a minute, don't conclude like that. See, there is a very interesting question here. I am attaching one frame here and another frame here. Okay, now are these two frames equivalent? Equivalent means, if this is at rest, this should also be at rest. If this is in motion, this is also in motion, like that. Are they equal?
Sir, no, sir.
Why?
If I momentarily, no, sir.
Momentarily, I said momentarily it is at rest. But in the sense, even momentarily, if it is at rest, okay, if I attach frames here, are they both same?
No, sir, no, sir.
Why?
Sir, the instantaneous, that frame attached to IR, sir, it can be accelerated. Sir.
Who told you?
Can this,
How did you guess?
sir, like inertial frames?
What inertial frame? Your
Sir,
guess,
it can be accelerated.
why did you guess that it is accelerating? No, why did you guess it can be accelerating?
Sir, like it's the only possible explanation.
It's the only possible explanation. Sure.
Yes, sir.
So it is, you have guessed it like that, right? Can you give me another example where the particle is momentary at rest, but if we attach frames of reference to the particle and ground, okay, then you can convincingly say it is accelerating and this is not accelerating.
So when a body is decelerating, its velocity may become zero at a moment. Sir.
When a body is what?
Decelerating.
Body is accelerating. Give one example. Good, very good. You give one example. Like some very good example which you know.
Sir, the car, sir, it is accelerating, sir. Now, if we look at the tire of the car, wheel of the car, we can find an instantaneous acceleration, sir, IR, sir, but it will be accelerating. So,
difficult. See, the same. This only you are telling now. You know, this is car tire. You look at it.
Sir, that
give a simple example where the particle is at rest momentarily, but if you attach frame to that and ground, it is accelerating.
Sir, bus stand that pendulum is accelerating bus stand.
Where will you attach the frame to that?
A person inside the bus stand, a person outside.
No, you got it wrong. Neela was coming to the point, but she didn't give the right example.
Sir, if we consider a body which is constantly decelerating, sir.
You give me live example, man. See, you are all considering a body, so I can have 101 considerations here. Simple, yeah. You throw a stone up.
Yes, sir.
So momentarily, when it comes to the highest point, momentarily this is at rest, isn't it?
Yes, sir.
But this is accelerating. So if you attach a frame to this, and if there is a frame to this frame, and with respect to this frame, at that instant, this frame and this frame are equivalent. At that instant, both of them are rest. Understood? At that instant, both of them are at rest. But this is accelerating because the particle going up and coming down will always be into the acceleration 0.
Yes, sir.
Yes, sir.
So situation here is also same. Situation here is also same. Got it?
Yes,
Okay? Fine.
yes.
Now I will give you one more situation. Okay? Now try and see. One more situation I will give you. Now, supposing this body is rolling. You know rolling now? I think I already told you it is rolling. So, and there is mu s here. It is rolling. So, it is rolling. So, then at a given instant of time, this will be the IC1. Correct? Hello?
Yes, sir.
So at the next instant, this will be here. So this will be IC2. Right? This will be IC1, this is IC2. This is rolling. Right? So I pushed it and I left my hand. So it is rolling. I pushed it and left my hand. It is rolling. Got it?
Yes, sir.
Yes, sir.
I am not holding my hand onto that end. Now, this IC1, this IC2. There are two instantaneous center of rotations. At this instant, time t1 it is here, time t2 it is here. Okay. Now, if you attach frame here and frame here to this. Now, what have you got to say about the instantaneous frame of reference? Are they equivalent?
So the surface is frictionless.
ಅಲ್ಲಮ್ಮ ಅದು ಫ್ರಿಕ್ಷನ್ಲೆಸ್ ಅಂತ ಹೇಳಿದ್ರೇನು ಓನ್ಲಿ ಟು ಹೋಲ್ಡ್ ಇಟ್. ಐ ಥಿಂಕ್ ಯು ನೋ ರೋಲಿಂಗ್ ಫ್ರಿಕ್ಷನ್. Sorry, now I explained to you in the last class. Rolling friction, kinetic friction and all. It is only static friction. It is rolling without slipping.
Yes, sir.
So
They are equivalent, says Arun. What about others?
Position with respect to ground and everything else is same.
Everything else except position, everything else.
Isn't it? So therefore you see at every instant of time, see at every instant of time DC is at rest only. IC at every instant of time is at rest only.
yes, sir.
Yes, sir.
But that point, if you take, that point is moving with some velocity VC.
Yes,
See,
sir.
for us, you know, if two frames of reference are moving with constant velocity, then it is still an inertial frame for us.
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
See, now this reference frame is moving with constant velocity.
Yes.
It is still an inertial frame. For us, if it is only accelerating, then we call it as non-inertial frame. Okay, so you can see here, you know, in this condition it is equivalent. In this condition it is equivalent. Okay, but one more thing here is that this point here is having acceleration, no doubt, but it is also having velocity. Hello.
Yes,
At this instant. So the fact is that if you are measuring the velocity of this point with respect to this frame, if you are measuring the velocity of that point with respect to that frame, then you can do the velocity measurements easily. Okay. Only thing is, if you want to do the acceleration measurements, then you have to consider it as non-inertial frame, and you should handle that. You should use pseudo forces and handle it.
Yes, sir.
That is the aspect that I wanted to discuss. Okay, so fine.